Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Katie Merrell with us today. Hey, Katie.
Hi, thank you for inviting me.
Oh, well, thank you for putting together such a lovely research note. And I'm glad we're going to go over it. So it's really cool. Katie, where are you located at? What's your geolocation?
I'm in Atlanta, Georgia.
Atlanta. All right. I spent some time in that area at one point during one of my postdocs. I was actually in South Carolina. I was in Clemson.
Oh, it's beautiful there.
But yeah, and so one of the only disadvantages there was an hour and a half to the Atlanta airport. So yeah, I would come into Atlanta fairly common to fly out or in and out. But yeah, I like the area. It's very nice. Very nice. Where are you in your trajectory?
So I'm a fourth year, starting my fourth year in grad school. Looking to hopefully submit my dissertation 2023 spring.
Awesome. I look forward to calling you Dr. Merrell.
Oh, thank you.
Awesome. That'll be fantastic. So Atlanta, how is the summer in sort of the South this year?
Warm.
Warm?
I'm originally from Seattle, so used to sort of generally temperate, rainy weather. Summers, hit in the mid 70s. Atlanta's a bit warmer than that, but the summer storms are pretty cool. They get pretty intense.
Yeah. They're short and very intense. Boom.
Yes. Yeah. Suddenly. Yeah, you see people walking in the grocery store soaking wet when you were just outside and it was sunny.
Yeah. Pretty wild.
So you're in Phoenix. How is it there in August?
Let's see. It is August 27th, 2021, and we are probably going to peak out at about 112, 113 today. So 40C, 41C. The humidity is still, so the rainy season in Phoenix is July and August. That's when our humidity goes up because you get the Gulf Coast moisture comes up. But we're starting to dry out, so the humidity is down a little bit today. But we are still gonna, still 112.
Yeah.
There's only so much you can say about, oh yeah.
Oh my gosh.
But it's, on the other hand, the winters are absolutely lovely in Phoenix.
Oh, I bet.
It's great.
Awesome.
So Katie, what do you like to do for research?
So I like to measure supermassive black hole mass using stellar dynamical modeling.
Okay.
So the two most popular methods for measuring supermassive black hole mass are stellar dynamical modeling and reverberation mapping.
Yep.
So I'm doing one of the two. So resolving those innermost regions of the galactic bulge and trying to measure mass from that. Yeah.
Very cool. Good. And that is going to bring us to this very lovely research note. A comparison of stellar kinematics derived from two Gemini NIFS reduction pipelines. And Katie, take us away.
So this is an intermediate paper, sort of to my the next paper that I'll be hopefully submitting in spring of next year. That will actually be measuring the supermassive black hole mass of NGC 6814, which is the galaxy that we used for this paper. And I'd like to give a special thanks to my advisor, Misty Benz, Dr. Misty Benz, who's the second author on this paper, and our collaborator, Dr. Janelle Walsh. And so she was the one who developed this new pipeline that we'll be talking about in this paper. She and her team. So we used data from the Gemini NIFS, so the near infrared integral field spectrograph. Yep. And so we used that data. We looked at, our observations are from NGC 6814. This paper is kind of short, so we were limited to about 1,500 words and one figure or one table.
Yes.
So there was a little bit of an effort there to make sure that we were under the word count. So there's a little bit more that I can probably explain. We had to be very concise. We'll talk about, I guess we'll go into the introduction. And so briefly talking about just our observations coming from the spectrograph. So we're looking at like I said, the very innermost region of NGC 6814, which is about 21.5 megaparsecs away. Okay. And so this has a 3x3 arcsecond field of view. So that translates to about 300 parsecs across.
Okay.
in that region there. So we're looking at, so what we're doing here is we're looking at the motions of the stars in that region, in the potential well of the supermassive black hole, to see what the influence of that black hole is on their motion.
Okay.
Let's see. So originally we used to do the reductions for NGC 6814s. We used the Gemini NIFS. There's some reduction scripts on the Gemini NIFS website that are very widely used for doing these types of reductions from the spectrograph. And then Janelle Walsh and her team looked to mitigate some of the limitations of that reduction pipeline by developing a new one. Another thing to note that we did mention in this paper is that Janelle's and her team's pipeline is actually fairly automated, which is really nice. So you can just sort of let it go, and it does a lot of the steps itself, which was really helpful. And there you can go in and create some stops yourself to look at the data in the in-between steps to make sure that you're getting the results that you're looking for.
Right.
But yeah, so some of the limitations from the original NIFS pipeline is so there's not much variance propagation. It sort of stops where you do the Telerik corrections. So Janelle's team made sure that the variances were propagated through the entire pipeline to the final NIFS data cube that you get at the end. So the end of the reductions, so you get the observations from the spectrograph are in 2 dimensions. And then you end up getting through the pipeline, the reduction pipeline, a data cube. So you have the spatial in 2 dimensions, and then you have a spectral dimension in the 3rd dimension. So you have X and Y spatial dimensions, and then again the spectral information 3rd dimension. So
cool.
So some of the other limitations are there's no flux calibration that's implemented. There's no heliocentric velocity corrections, and there's no way for the original pipeline to combine the science exposures into a single data cube. So that's left up to the user to do some of those. So there are some other little improvements that they had made, but those are some of the big ones that they tackled and incorporated into their new pipeline. So that was really exciting. So we were told that this was being developed when we were doing the original reductions, and then their team completed their work right around the time that I'd finished the original set of reductions. So it came at just the right time so that we could use both. We hadn't planned on it, but we were able to use both and then write this little paper about it to get it out to the community about this new reduction pipeline. That, spoiler alert, at the end of the paper, we do recommend the new pipeline over the
Shocking.
Oh no.
So surprised.
I gave away the ending. So we'll talk a little bit about some of the major improvements that this pipeline made. Okay. And one thing we did too is, so we got a better comparison of the end results when we extracted the kinematics. We made a couple of modifications to the original pipeline ourselves that sort of better matched what Janelle's pipeline did. So although we didn't incorporate flux calibration, we did incorporate our own version of variance propagation and Telerik corrections, heliocentric velocity corrections, and combining of the science exposures. Okay. So the first thing that this paper talks about is the bad pixel masking using the NIFS mask called NF-fix-bad. So very to the point. It's easy to see what that one's supposed to do. So what the original pipeline does is it will, if it detects a cosmic ray or a bad pixel, it'll interpolate using the 2 pixels on either side over that pixel to just eliminate that noise spike or whatever happened to come across there. Okay. But in the variance extension, what the original pipeline does is it just flags it and sets it to a really high number. And so we were getting all of these noise spikes in the variance data. Yeah. Mm-hmm. And so that was kind of odd. And then so you can see that, and I'll explain what these in the figure below, I'll explain what sort of those have in them, but we can definitely see, you can see the top row versus the bottom row, the bottom 2 rows. You can see some, especially in the chi-squared plots on the very right, you can see there's some not so much in the chi-square plots, in the velocity plots, sorry, on the far left, especially in the bottom plot, you can see there's some striping like in the bottom right and left corners of that far left bottom plot. And that's coming from that NFFix bad task that sort of doesn't really treat the variance propagation the same way, or the variance data in the same way as the science data. So the new NFFix bad task that they had written just treats the variance data the same way as the science data and interpolates over that noise spike so that you just get something that makes a lot more sense than just setting that pixel to a really high number in the variance data, which was kind of odd. So they fixed that. So that was really good.
What is let me just ask, what is A, B, and C here?
So we can talk about this. So A, B, and C. So the top plot is so these are the kinematic maps. So going from left to right, we have the velocity maps, and you can see the color scheme at the bottom there. Sort of showing, and you can see so we're looking at about 2x2 arc seconds here in this region. And so the velocity plots are on the very left. And so you can see that those are showing about 1540 to 1610 kilometers per second. And that's just, that's just the line of sight velocity in each pixel that we're seeing here in this region. Sigma is the velocity dispersion. So the random line of sight motions of the stars in that region. So that's what we're seeing there. And then I'll talk about this in a little bit. So H3 through H6, those are Gauss-Hermite terms. And so in the kinematic analysis, we use an algorithm developed by Michaela Capillari called PPXF, a penalized pixel fitting. Cool. And so when we're measuring the line of sight velocity distribution, we're looking at so we can fit that distribution usually with a Gaussian. It's very Gaussian shaped, but we also want to sort of do a little better job than just fitting with a pure Gaussian. And so we use these Gauss-Hermite terms, which do a better job of sort of fitting the more askew or flat or peaky sort of shapes. And so we're looking to fit those a little bit more closely. And so that's what those Gauss-Hermite terms are for. And then the far right plots are the chi-squared plots. And then you mentioned what A, B, and C are. So A are the kinematic maps for the new pipeline. Okay. B are the kinematic maps for the new modified pipeline, or sorry, the original modified. And then C is also the original modified pipeline, but using the old NFFix bad task. So B and C are mostly the same, minus using that one IRAF task. Right. And so you can definitely see, even between B and C, that extra striping on the side of the velocity plots. And that's the only difference between those two plots. Yep. So that was a big change. That was really important. So that's why we put it first.
Nice. Okay.
So if we go back to the paper, we talk about the next, let's see, we scroll down a little bit farther. Awesome, thank you, there we go. So a little bit, scroll up just a little bit, sorry about that. So one of the things that like I mentioned before, that the original pipeline on the NIFS, Gemini NIFS website doesn't incorporate is the Telerik. Well, they do a version of Telerik corrections that we actually changed in our original pipeline, and Janelle's team changed in their new pipeline. So the Telerik corrections are done using a black body curve and just interpolating over the strong absorption lines, and doing that with just by hand using an IRAP task called splot. And so what we did in our original modified pipeline is we used a program called XTELCore, which uses a Vega model spectrum, an AO5 star, to simulate the observed star spectrum so that we can eliminate the stellar features in the spectrum, and then we can just get the Telerik features, and then we subtract that from the observed galaxy spectrum.
Yep.
And then the new pipeline uses multiple A-star Cruise models. And so that does even a better job than just using one Vega model, by using many A-star models to eliminate those stellar features. So you're just left with the Telerik features.
Okay. Okay. Good.
So go ahead. Sorry.
I'm with you. Good.
And then one thing too that we mentioned in the last sentence here was that the new pipeline actually takes one of those star frames for the Telerik stars, and it uses that later to do the flux calibration. So that's one thing that the new pipeline does as well, is flux calibration, and it uses one of the Telerik stars that it converts into a data cube. It's usually, I think it's the first star on the first night that is used, but you can change that. You can go into the code and make it how you want. And then talking about too, the propagating the variances. And so that's one of the things that the new pipeline does as well, is that we sort of, we made some executable CL scripts, irefs.cl scripts to propagate the variances through the end of the reductions that we just sort of added ourselves in there. But Janelle's pipeline automatically propagates the variances all the way through. So you can get your data cube and your noise cube at the end, and they're automatically there, and you don't have to add anything extra to get that information. Because it's really important to have that noise data, especially for extracting the kinematics.
Yep.
So, and then let's see, and then we can talk about the combining the frames at the very end. So one of the things that the original pipeline does is all of each galaxy frame is individually rectified into a data cube, and then those data cubes we combine into one final data cube.
Yeah.
And then the IRAP task doing that is called mcombine. And in that task, which is an advantage, is that you can incorporate a pixel rejection scheme. So even though we've done bad pixel masking earlier in the pipeline, there are still some bad pixels that get through. And so this is the step where in the mcombine task, you can set it so that it will do sort of any amount of pixel rejection. So when you're combining, however many individual data cubes you have, that it's combining those same pixels. You can reject, if you have 20 of them or 30 of them, you can reject 1, 2, 3, 4, as many as you want, and you can set it so that it will to like the maximum amount that you want rejected. The original pipeline. Actually, instead of, in addition to that, in the original pipeline, once when we're combining, we'll upload an offsets file. So all of the cubes, like the AGN is not centered exactly in every single frame and every single individual data cube. So the original pipeline only allows integer offsets. So just one whole pixel at a time, you can sort of shift each individual data cube and then combine them so they all line up.
Yep.
In Janelle and her team's new pipeline, a couple of things happen that in that step that are really important. So one is they actually combine, instead of combining individual data cubes, they eliminate that step and actually combine the frames, the individual frames together into one data cube in a single step.
Yeah.
So that eliminates a lot of possible errors that can come out of that. It's always good to eliminate steps. In addition to that, their pipeline also allows fractional pixel offsets, which helps retain spatial resolution, which is really important when we're looking at this really tiny region really far away.
Right. Cool.
So that was something that was really awesome that their pipeline does. And then the last thing that we mentioned here too is the heliocentric velocity correction. So the original pipeline doesn't incorporate that, and so we wrote our own script to correct for those heliocentric velocities. So there's an IRAP task called RV correct. So we determine the heliocentric velocities. So we have to take into account the motion of the Earth around the sun, since we are doing such precise resolving this region 21.5 megaparsecs away. So we really want to take into account that that doesn't cause any errors in our data. And the largest heliocentric velocity correction was, I think, around 25 kilometers per second. So it was really important to do this step. And so we wrote a script that we log rebinned the data from wavelength space into velocity space, and then we applied the velocity heliocentric velocity corrections, linear rebinned, and then log rebinned again, so that we can get everything binned correctly. Right. So and then again, Janelle's script automatically does this, so you don't have to add anything. And especially because I didn't mention it before, so our observations, a lot of people will have observations that are taken on consecutive nights for a week, a couple days, 2 weeks, however long they're observing for. These were taken over the course of about a year. Oh, wow. So we have, I think it was a total of 14 nights. We ended up being able to use 12 of them. The heliocentric velocity corrections were important, especially because they were so spaced out like that. Right. Throughout the course of a year. Yeah. Then we reduced once we were done doing the reductions with both pipelines, we used, I mentioned before, the penalized pixel fitting method to extract the kinematics. So we talked about a little bit about that here. So we made those kinematic maps by using this the PPXF algorithm to extract those kinematics. So basically, what we're doing is we have a set of stellar templates, because we know that most of the light that we're observing in this region is coming from GK and M giants. So we're really focused on those particular stars, and so we have a template, a bunch of templates. I'm trying to remember how many that are from GK and M stars. So we use those to if we convolve those with the line of sight velocity distribution, we can produce a model that represents the observed galaxy spectrum. And then what that algorithm does is then the one that best matches the observed spectrum is the one that is used. And so then we have we can recover the line of sight velocity distribution in that way. And that's where we use the Gauss-Hermite terms, the H3 through H6 terms to fit those profiles. And,
yeah. Okay, you're adding polynomials to it. Got it. I'm with you.
So then we, at the end, we mentioned here that we give the reasons why we chose to recommend the new pipeline. And one of them being that we actually looked very closely at our end results, and although they were really similar, there were a few differences that we noticed, including smaller chi-. So we saw similar chi-squared values for both the pipelines. The new pipeline showed smoother kinematic maps in general, right, and similar chi-squared values, but a more compact region of central values. So so you can see that region is more compact. So those two things, in addition to, we also produced a PSF image from the observed galaxy spectrum. So we actually subtracted. So we subtracted a slice of the data cube from the continuum, and we subtracted that from a slice of the data cube where the AGN is very bright. So this is in the K band. So at bracket gamma, that's where there's a giant broadened emission line from the AGN. So we subtracted those because we assume most of the noise is shot noise coming from the source. And so we produced a PSF image from both pipelines, and we found that in the new pipeline, that PSF was much smaller. And so that really proved that the spatial resolution is better maintained in the new pipeline. So that was a big one too, for recommending the new pipeline. In addition to a lot of the improvements that we had mentioned before. And one of the things too that we had mentioned before that we actually ended up being able to go in and figure out how to eliminate this problem is one of the things when I had mentioned the combining of the final frames and combining of the in the new pipeline, the combining of the individual data cubes in the original pipeline. Yep. And that we were able to do a second pixel or pixel rejection scheme. And so we were able to sort of eliminate some more noise in that step in the original pipeline. But the new pipeline wasn't using that same method for combining the frames. And so we were seeing some extra noise that from the new pipeline results. And so we mentioned in this paper that we recommend that there's some additional noise and that users may need to use something to clean up that extra noise. And we suggested here there's a clean parameter in PPXF that can be applied. But we submitted this in December of last year, so December of 2020. And since then, we've found a way to incorporate another bad pixel masking step when we're combining the cubes. So we went into the code and sort of we made a couple of little changes there to scale the frames night to night, and then also add another bad pixel mask using the data quality extension. So we were able to eliminate a lot of that excess noise that we were seeing, and so that was a really good step forward too in the right direction. But yeah, this was really nice being able to use two different reduction pipelines. This is the first time I'd ever reduced anything. So yeah, this was good being able to use this. And yeah, it was a really short paper. So hopefully there wasn't too much detail.
Okay. So Katie, thank you very much for sharing that research note with us. That's very nice. You touch on it. In fact, you touched on it a couple places there at the end. So let me ask you to give it a future look. That could either, where do we go over, let's say, the next year or two in either, improving this data pipeline even more. And then if you would like, presumably this data pipeline will be used on some article that will be forthcoming. So you can talk about maybe where that is headed. So
okay. So yeah, this paper was sort of an intermediate step to a paper that we're hopefully going to be publishing in spring of next year. Okay. So I'm in the middle of writing that now and doing some of that work. So in that paper, we'll be presenting a measurement for the supermassive black hole mass of NGC 6814 using like the stellar dynamical modeling method. So and this was reducing the data was a step in that direction. So we wanted to be able to get this. We published this paper so we could sort of get that information out to the community if people wanted to use this new pipeline for reducing data. And so, but yeah, in this paper, in the new paper, we'll be using this to, so we've done this to do the reductions for NGC 6814, and then those are the reductions that have moved forward with to extract the kinematics and then do the modeling. Okay. So that's what we're working on now, and so we've actually been able to work directly with Eugene Vasilev and Monica Valeri, who have developed a new dynamical modeling algorithm called ForStand, which is really exciting because it's the first modeling method that will be able to model a bar. So produce a triaxial model. Oh, okay. Yeah. Mm-hmm. Model a bar, which is really cool because a lot of galaxies do have them, and so that's a really great. It's a source field orbit superposition method. So modeling the orbits of stars in that region in the potential well of the black hole. So to measure the black hole influence on their dynamics. Yeah. So that's really exciting. So the really important thing about this about this research in general is that the two most popular methods for for measuring masses in supermassive black holes is stellar dynamical modeling and reverberation mapping. So reverberation mapping is it focuses on the time domain. So you're measuring basically the light echo from the accretion disk in the broadline region clouds. So the viscous heating and then you get emission from the accretion disk, and then those and then they photoionize the clouds in the broadline region, and then those recombine, and then from that you can measure basically the size of the broadline region, and then from that then use the virial theorem to measure the mass. And so that's in the time domain. One great thing about reverberation mapping is it's basically distance independent. So depending on how far away it is, you're going to have to wait a long time for that light to be echoed from the broadline region. Right. But it essentially doesn't have any constraint on distance. With stellar dynamical modeling, you are trying to resolve the bulk motions of the stars in the region near the black hole. And so stellar dynamical modeling is really limited to about 100 megaparsecs. You're really looking at just galaxies that are close by. The problem is that reverberation mapping requires that we're using active galactic nuclei, so AGN, yes, which are very rare close by. So most of the galaxies that are close by are quiescent, so they're not continuously eating matter. And so there are only the galaxies that are actually able to have supermassive black hole masses measured using both methods. So it's really important to do that. Yeah, so you can, so we can better constrain some of the parameters, identify any biases in either of the methods. So you have completely two different data sets. And if we can measure the same mass with both methods, or even if they're different masses, then we can sort of better hone one or both of the methods that we're using to measure those. And so NGC 6814 will be the third galaxy ever published to have a mass measured with both methods.
Awesome.
So that's kind of fun. It's really exciting. And then the next galaxy actually that I have reduced and extracted the kinematics from, I haven't started modeling, is NGC 5273. So that will be number 4. So that's really exciting work. And so this was sort of an intermediate paper to that bigger paper that will hopefully be published spring of next year.
Awesome.
But as far as like other reduction methods for NIFS data, I'm not sure what else, I'm sure there's other methods out there, but this was a big step in the right direction to sort of get some of those limitations dealt with.
So if people want to access the features of the new pipeline, I imagine these are publicly available, or you put it up in some repository within NIFS, or?
So I think they're on a GitHub.
Okay.
So yeah, so I don't know the exact.
Oh, I will put a link to it in the description below the video. So if people want to.
Okay, good. Yeah. So, and that's really exciting. But yeah, so yeah.
Well, thank you so much. And given the future projections there, I'm looking forward to some pretty awesome papers.
Thank you.
Over the next couple of years, and it'll be a great thesis when you get there.
Thank you.
Cool. Thank you. And that'll do for this one. And thank you, everyone. I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.